All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have a double feature, actually. We have Dr. Jean-Pierre Croix and Dr. Federico Rossi, both from the Jet Propulsion Lab, the NASA Jet Propulsion Lab. I briefly want to introduce both of them. So I'll start by Federico, just because I have the bio of Federico in front of me. But Federico is a robotics technologist with the multi-agent autonomy group within the robotics section of the NASA Jet Propulsion Lab. And there he led the multi-agent autonomy team for NASA Coordinated Autonomous Distributed Robotics Explorers, or in short, Cadre, which you see in the cover slide for today's talk. And this is a mission that will deliver a team of 3 autonomous rovers to the moon's Reiner Gamma region in the coming year. Something about Federico, he obtained his Master of Science in Space Engineering from the Polytechnic of Milano, and then moved to California to obtain his PhD in Aeronautics and Astronautics at Stanford, working with Marco Pavone. Broadly speaking, his research focuses on decision-making under uncertainty, multi-agent robotic systems, and operations of autonomous agents, and applications range from planetary exploration and earth science. And in the past, he also worked on autonomous vehicle fleets for transportation, which is actually the way I got to know him in the early days. The second speaker from today is Dr. Jean-Pierre Croix, who is the robotic systems engineer in the Maritime and Multi-Agent Autonomy Group at NASA JPL. He joined JPL after completing a PhD in electrical and computer engineering at the Georgia Institute of Technology. And his research is focused on new control techniques for large-scale robotic systems, such that humans can easily and effectively interact with these complex systems. JPL is working on these topics for new challenging applications, including Cadre and other missions probably in the future, I guess you. And currently, Jean-Pierre is the Cadre principal investigator. So today, they will give a very exciting talk about multi-agent autonomy for a team of rovers on the moon. I have seen a previous version of this talk, and I was amazed by both the thoroughness of the result, but also the coolness of the demos and applications. And therefore, I had to invite these guys to Autonomy Talks. And therefore, I leave you the stage, guys, and I'm very excited to see more about it.
All right, thank you. And yeah, thank you for both the invitation and the wonderful introduction. So let's dive right into Cadre. So before we can talk about having an autonomous team of robots, I really got to give a huge shout out to the team of people that made this possible. We have a lot of amazing engineers, including Federico sitting right next to me, that cover a really wide range of areas, right? So we cover things like flight software and systems engineering and thermal and mechanical and power, and then certainly what we're going to talk about primarily today is autonomy, both in terms of the onboard autonomy for these rovers, as well as the multi-agent autonomy, which covers having them to work together as a team, as we do as people. So let's first talk about what is Cadre, right? So Cadre is a technology demonstration of multi-agent autonomy that's going to go to the moon. We're funded out of NASA's STMD game-changing development program, and we're currently manifested as a payload on a commercial lunar payload service lander built by Intuitive Machines, and we're going to be their third mission. So that's usually called IM3. And the place where we're headed on the moon is called Reiner Gamma, and Reiner Gamma is fairly well known for those fantastic lunar swirls that you can see on the lunar surface, where the dark and light regolith is mixing. And again, we're going there sometime next year. So the current launch date that's been announced is sometime at the end of 2025. And what are we going to be demonstrating? I mean, I broadly said, it's team autonomy, but specifically what we focused on are really 2 key capabilities. One is the ability for the team of rovers to work together to explore an environment without being given a whole lot of prior information. So they have to go build up a map of the surface. And then also what we wanted to demonstrate is that this is, a new technology that's able to perform new types of science. And specifically, what we focused on is something called distributed measurements, or the case where you have robots that are in multiple places taking measurements at the same time in a coordinated way. And specifically, I'll talk a little bit about how we do that with something called a ground penetrating radar, or GPR. So why do multi-agent systems at all, right? Usually we send one rover out somewhere. Why would we, divide up the valuable mass and volume that we have on our missions into multiple pieces and have maybe smaller robots, but more of them? Well, the idea is really that, we believe that we're stronger together, right? So having multiple agents in a system affords new capabilities. And really the way that we think about it is in three different kind of thrusts here. So one is certainly at the top is what kind of new science can we enable? And what kind of new data can we collect? And again, we're focusing on the ability for multiple instruments to be in different places, but take measurements at the same time. Secondly, you can think about it in terms of what kind of access can you achieve, new access that you can achieve with these systems, right? So if you have multiple robots, can they maybe form a communication chain and access something like a lava tube in a lunar pit, or in the Martian equivalent of that? Or maybe you can afford to send one of the rovers into a one-way trip into a permanently shattered crater where it can send you the data back, but it doesn't necessarily need to get back out of there. And the system continue to operate because it's got more agents available to it. And then certainly you can also think of it in terms of kind of the practical things where you gain more efficiency, more flexibility in the way you do your missions, and also things like resiliency, right? So you're able to have degraded performance rather than just, either you have the rover or you don't have the rover. So a little bit of history. This technology has been in development for quite some time. It started roughly in 2015 to 2017 when GCD funded a project called Puffer. This was actually before I joined this technology effort. We had a bunch of hardware engineers build a very small and capable robot called a Puffer, or Pop-Up Flat-Folding Explorer robot. It really demonstrated that you could have quite a bit of capability in a very small package. And really the nice side effect of that was that, now there was trust in like, hey, we can do things with small things. And the nice thing is that because they fit into a small volume and they're low mass, maybe we can send more. So the initial idea was actually to package up these into a shoebox, like 5 or 6 of them, and attach them to a future Mars rover and have the Mars rovers to go deploy the puffers. So folks got really excited about the prospect of multi-agent systems around that time. And I had the opportunity to kind of join them at the tail end of the puffer development and then kick off something called Autonomous Puffer, which was basically take the puffers and add autonomy, right? So add the team autonomy component. And there we've really focused on the exploration, the cooperative exploration component. So how do you build a map with a bunch of robots that don't have a prior map of the environment? We had interesting kind of constraints added to that, such as they have to maintain line of sight communication at certain points of the mission so that they can kind of get all that data back to the base station throughout the mission and not just at the end. And then we developed that technology and demonstrated it in the field or in our labs here, outdoor labs here at JPL. And we were funded then to go and turn this into a full flight system that could operate on the moon. And that's what Cadre is. And that's what we'll talk about today. So let's talk a little bit more about what we're enabling in terms of the science. So today, the way that you do ground penetrating radars is on the left-hand side. That's a picture of the RIMFAX ground penetrating radar that's on Mars 2020. So it's currently sitting on Mars, taking ground penetrating radar images. But what we're looking to enable is a new dimension, which is to use multiple ground penetrating radars and have them work in concert to take measurements. So again, why would you want to do that? Why is it not sufficient to just have a single ground penetrating radar? Well, the reason for that is that you're limited to doing monostatic measurements with a single ground penetrating radar. You can basically drive a ground penetrating radar across a path, and you can integrate that signal and get it to the slice of the subsurface. You could maybe try to push and do like a lawnmower pattern and try to do 3D, but since these systems start drifting, this gets just worse and worse, right? You're just integrating error upon error. So what you see on the right-hand side is with a multi-static ground penetrating measurement, you first of all, you distribute the error across the team, and then maybe you even have some techniques to reduce the error across the team that we'll talk about. But effectively, you're now driving 3 systems with a ground penetrating radar, and you can split up that task of doing a 3D measurement. But the one thing that you really get out of here is these cross tracks. So the ability for one ground penetrating radar to listen to the reflection of another ground penetrating radar and know the separation distance between those, that really enables something called a multi-static measurement, and that gets you these really nice 3D subsurface images that I think we would all really be excited to have and allow us to learn more about our solar system. And really what autonomy then needs to do is it needs to be able to drive these 3 rovers in a formation with certain tolerances so that the formation doesn't just deviate, but stays with certain separation, which correlates to the depth at which the ground penetrating radar is doing its measurement. So what technologies did we have to advance, right? So what we had to advance are really 3 key things. One was the ability for the team to keep track of where they are and to help each other in doing that. We do that via these inter-rover distance measurements. So the robots have a radio that allows them to measure the distance between each other, and we use that as a way to do post-graph optimization in the absence of visual loop closures. And then in the middle, we had to come up with some extensions to existing motion planners to go ahead and be able to both plan for the team through a cluttered environment, but then also have them track a trajectory both in time and space, since they have to be in this particular configuration at a particular time. And then lastly, we also had to develop technologies for them to be able to really share this data and to keep track of the data and have that in a place where they can use that for planning, right? So those are really the 3 key multi-agent technologies that had to be developed into a flight system. At the bottom, just for your reference, I also included other technologies that we developed as a way to support and enable these capabilities. So we needed more than just these 3 things for a fully working system. So a little bit about the system. This is the picture of the Nova Sea lander by Intuitive Machines. We're going to have 3 of our rovers on this lander on 3 sides of this lander. We actually have a 4th agent called the base station. So it's basically one of our rovers without the wheels that's permanently attached to the lander and is not going to go onto the surface. But our 3 rovers are going to rove around on the surface. So they get lowered via a deployer and get to roam around. We also have a situational awareness camera, so we should be getting really good pictures and GIFs of our rovers roaming the surface of the moon next year. Here's a close-up picture of our flight rovers. So you can see here is just a variety of components that we have kind of on the top deck. We have the white thing is the radiator for us to reject heat from the system. Then on the left and right are the solar panels that get deployed. Basically, they sit on top of the rovers and they deploy open. Again, since we're going equatorial, most of the sun is going to be overhead, which is why our solar panels are facing up. And then we have antennas all across the top of it. So we've got 2 ground penetrating radar sync antennas. We have an antenna for the mesh network radio, so for the robots to talk to each other. We have the ultra wideband ranging antenna, so that's for time of flight range measurements. It's a little bit difficult to see, but there's also a sun sensor right next to one of the GPR sync antennas. So quite a bit of hardware, even just on the top of the robot. And looking inside, this is kind of an inside look at our robots. On the left-hand side, you can see some of our PCBs and the harnessing for one of the rovers. And on the right-hand side is a CAD model showing you kind of the inside of it. We have front and rear stereo cameras. We have an inertial sensor measurement unit. We have a sun sensor, as I talked about on the previous slide. So those are kind of key sensors for an autonomous robot to have. And then speaking of just components on here, I think one really exciting thing about our mission is because we're kind of a technology demonstration. It's given us allowance to experiment a little bit more with kind of the selection of components that we got to pick for the hardware. So we're running a voxel embedded computer made by Modal AI. It's based on a Snapdragon 821. So basically a cell phone from maybe like 2016 or so, which is quite a bit more compute than we typically get. And we also have off-the-shelf camera sensors, motor controllers, radios, FPGAs, and all that kind of stuff. So it's really exciting to be flying some stuff that you can buy off the shelf, and then maybe next time when you go build your own lunar rover, you can have some confidence that those components will work for you on the moon. Then here is a really fun slide. I've shown you, pictures already of the completed flight rovers and the system, and you might think, we just like sat down, designed it, and built these things. But we actually went through quite a bit of iteration, and our system has undergone some changes since the very beginning of the project. So, for example, we experimented with things like suspensions at the very beginning of the project, but then had to make do without a suspension because we figured, hey, we can traverse the lunar environment with a fixed system, and it saves us some mass and complexity. The same thing happened with the camera masts. Ideally, we know that we want to have the cameras as high as possible for the robots to be able to see as far as they can. But it turns out that added complexity and risk because you have to now figure out a way to deploy a mast and all that kind of stuff within the volume that we had. So that went away. We also had illuminators, but then that drew too much power. And we figured we'd be operating mostly during the daytime anyway, so we didn't need that. So one really nice way of saying that is our project system engineer called that a continuous optimization of compromises, which I think is a great way to phrase that, and something that I'm going to keep carrying on to my future projects. And then lastly, actually, there was one more, which if anybody's seen our logo, it has like 4 stripes that used to be at the very beginning. I had envisioned that this project would have 4 rovers, because that's kind of what we thought we could do with the payload constraints that we had. But it turned out over time that rovers needed to grow a little bit to survive the lunar environment, so we became 3. But I was able to figure out that we still have base stations, so there is 4 agents, so the logo did not have to get edited. The logo has been there since the very beginning of the project.
All right. Yeah, so let's talk about the autonomy architecture of Cadre. There are many drivers that went into this architecture in the selection of how the agents interact with each other. I want to mention 4. First of all, we wanted to be able to encode complex behaviors within the agents. So if you're familiar with all the swarm architecture, that is great if you want to do coverage or if you want to do flocking. We wanted to do distributed planning and scheduling. We wanted to do more complex behaviors. That was the first driver. The second driver, which is key for a tech demo, is observability. We wanted to, at any point, be able to say with high confidence, this is what the system is doing. This is what the rovers are trying to do in a way that would make sense to somebody programmatic in the room who's asking, how are you spending my X million dollars on it? So we wanted a system that was observable. We wanted to be resilient. We did not want to build a single agent system with weird actuators. We wanted to be able to lose some of the agents, potentially any agent, and recover, at least in the autonomy. And we wanted to push as many decisions as possible down to the individual agents and generally reduce communication between the agents for 2 reasons. One is we are a tech demo. Historically, multi-agent systems communication is the bottleneck. So demonstrating that we can do the things we do with low communication goes in the direction of showing these technologies really work. The second reason is the RF environment of having antennas down to the ground in Reiner gamma. We don't know. We haven't been there. I don't think we've had antennas so close to the ground. We know regolith is evil in more ways than one. It's electrically charged. It gets everywhere. So reducing communication is a way for us to protect ourselves against potentially more interference than we expected. And so the architecture we came up with looks a bit like this. Of course, we have ground ops at the top, and the kind of commands we send the rovers are, hey, team, go explore that region, or hey, team, go drive information across this area. They're commands for the teams, not for the individual agents, and they're very high-level commands. These commands go to the leader. Who is the leader? We're going to talk about that, but the rovers pick a leader among themselves. On the ground, I mean, we can influence who the leader is, but the rovers at any point have a leader. It's not decided in advance. And this gives us resilience, because if we lose the leader, the rovers will automatically elect a new one. The leader comes up with a plan for the team. It comes up with, it makes all the decisions that require coordination. This is when the robots are awake. This is when the robots go to sleep. If we are exploring, you get this region, you get this region, you get this region. If you're driving information, we're going to talk about it in about 4 slides, but any decision that requires coordination is made on the leader. And then the outcome of that is pushed down to individual agents. For exploration, that means that every agent, every rover receives a region, and then they explore that region as they see fit. For formation, again, we're going to talk about it, but it will mean that a rover is trying to hit its marks. And so long as it hits its marks, which will become clear in 4 slides, it doesn't have to bother anybody. The rovers are continuously talking to each other to check whether the leader is alive, and if the leader is no longer able to discharge its duties, to come up with a new leader. That is very low bandwidth. Every other communication is only done at key points where we need the information to be transmitted to the leader, typically when the rovers are stopped, so we're a little less scared about interference. And then every rover has a surface mobility stack that they use. Did I miss anything in this slide? No, okay. So in more detail, this is what our autonomy, this is actually a software diagram, a diagram of our software blocks. Ground operations only talks to the leader. Notice this arrow. The leader has a strategic planner that makes, scheduling decisions. This is when we go to sleep. This is when we are awake and drive. This is when we are awake, but we don't drive because we have to cool down a little bit. The strategic planner is able to invoke a team planner that makes geometric decisions that involve the entire team. Then these decisions are communicated to the agents, which elaborate them and do as much as possible locally. Who is the leader? The agents decide by themselves through leader election. At the core of the architecture is a distributed database, which we built on SQLite, that allows the agents to share information. Now, if you're familiar with shared word approaches, you may think, oh, all the agents are writing, and there is some Raft-like process that synchronizes information across all the agents. That's not how we're doing it. Agents write into their DBs. By default, the databases are out of sync because every agent will have information that has not been sent to anybody else. When we need information, the onboard autonomy triggers a synchronization at key points. So for example, right before we come up with a schedule for the team, we ask every rover, hey, what's your temperature? What is your state of charge? Because we need that information. Right before we divide up a region to explore into subregions, we ask the rovers, hey, send me your maps so that we know what everybody has seen. If that doesn't work out, if the databases are not consistent, that is okay. The system, a lot of work went into designing a system that could be suboptimal, but still make good decisions in the face of lack of DB synchronization. What else? At the single agent level, which is the bottom pane of this diagram, we have state estimation, of course. We need to know where the robots are, and we do that with 2 modules. We have a visual inertial solar odometry. We use stereo cameras, we use inertial. Interestingly, we don't use wheel odometry. Fun fact, that's because we don't have a suspension. So at any one point in time, at least one of the wheels will be off the ground, and compensating for that would be hard. If you've done visual inertial odometry, you know that you need a compass on the ground to know which way you're pointing, otherwise you'll get drift. Well, compasses don't work on the moon, but we have a sun sensor that looks at where the sun is in the sky, and through some maths, knowing the time of day, where the sun is, it figures out the heading, and the attitude of the rover figures out the heading of the rover. And then periodically, we continuously collect ranges between the agents through our radios, and periodically we use those ranges to re-optimize, to do global pose optimization and re-optimize past and current poses of the agents. We use those stereo images to build a dense 3D reconstruction of the environment, which we then turn into a 2.5D map for every agent. We'll talk in a moment about those maps are merged across the agents, and this gives us a knowledge of where we are, what is around us, that we can use to do motion planning. How do we use this? How do we use this for the C in Cadre is cooperative. What does that mean? It means that the agents have to work together to execute the commands that we give to the team. They have to go from, hey, folks, explore this region, to you go here, I've seen this already, so you don't have to go there, etc. They have to go from, hey, drive information across this area to, okay, you're going to be here at this time, and I'm going to be 2 meters left of you, and it's going to be 2 meters left of me, continuously. This is tricky. First of all, we don't really know where we're going. We have some idea of that the place we're going is not going to be super cluttered with rocks, and it's going to be pretty flat. But the best images we have from orbit are 1 meter resolution. Our robots, I think you can fit like about 4 robots into each pixel of the. Is that about right? Yeah.
I would say 1 rover per pixel.
1 rover per pixel, 60 centimeters.
Especially with the solar panels.
Fair enough. Okay, well, they're smaller than a pixel. How much smaller? We can talk about sub-pixel resolution, but point is we start out not knowing where we are. So for cooperative exploration, we are going to have to make these decisions. How do we split up the region to explore? Who goes where? For distributed measurement, the spec is drive information. The rovers have to be at a certain relative distance to each other. If they deviate too much by more than a few centimeters from that distance, we can still collect science data, but that data is going to be terrible. So we want to keep the robots as close to each other as possible while navigating a rock field that is initially unknown. And you can imagine what this looks like. If you have a very small rock, individual agents can drive around the rock without telling anybody else. If the rock is too big, then the agents have to collectively plan to move as a whole around this large rock. This is what we mean by cooperation. How do we do that? Well, let's start with planning and scheduling. To do things together, the robots have to be awake at the same time. And to do that, we reuse an existing scheduler that has been developed at JPL that's called MXX. Some of its heritage is actually flying as of last year. So after Cadre's start, some of that heritage ended up on Mars rover Perseverance. At the team level, we reason about all the rovers at once, and we schedule activities like go explore, go drive together, sync information to the leader, plan for the entire team, making sure that the robots have enough resources. The 2 key resources we track on every rover are thermal state. We don't want the rover to get too warm. If we drove continuously, we would cook the rovers. So we have to occasionally stop and let them cool down. And state of charge. If we drove continuously, we would run down the battery to the point where the rovers would be unable to discharge their duties. I'm not entirely sure. I think depending on time of day, you either cook them first or run down the battery first. And you can see at the top right a chart that hints at, in the earlier parts of the day, your main limitation is power. And then as you get in the middle of the day, you have all the power you need and then some, but thermal is the limiting factor. We plan on the leader for all the agents to be awake when they need to be awake together. When exploring, we don't care that all the agents are awake together. When driving information, well, yeah, you need every agent to be awake at the same time. And this planner is also able to react to loss of an agent. If one agent is no longer part of the autonomy team, the planner will sort of shrug its shoulders and plan for whoever remains, which I think is pretty neat and goes to the core of the resiliency requirement, which we talked about. How do we drive in lunar terrain? How do we drive information? Well, the classical approach is some control-based thing where you have a very fast control loop, like multi-hertz control loop between the agents. They check their position with respect to each other, and that works really well. We did not want to have critical loops that went across multiple agents at multiple hertz, because again, communication is the thing you should be scared of, I argue, in a multi-agent system. So we came up with something a little different. On the leader, we come up with a plan for the entire team. And turns out you can do that pretty simply. we started by saying, well, let's do, a baseline. Let's do something super simple. Let's run RT star on the joint state, on the 9-dimensional state of all agents, and use that to see how much we can improve with respect to that. Well, it turns out RT star is really fast, and 9 dimensions is a lot, but not that much. So that's what we ended up using. So we come up with a plan for all the agents that is a trajectory computed in a centralized way in the joint space. If you've used RT star, you know it's going to look something like you have up in the top left. I think this is RT star. Well, whatever. Mm-hmm. So quite a bit of work has gone into smoothing because, you could spend 10 milliseconds adding a few RT samples, or you could spend 10 milliseconds smoothing the samples you have, and it's going to be great. But then, does that mean that every time the rovers deviate from the trajectory, we have to replan? Absolutely not. That would be silly. What we do is once we have this trajectory, we build a tube around that trajectory. The size of the tube is designed so that if every agent stays within its tube, we do not violate the inter-agent distance constraints. And the tube is time-stamped. So from the perspective of an individual agent, the agent doesn't, we plan for the entire team, and then an agent gets a cue sheet. It gets a set of marks. Here's a tube. You have to be within this circle in the tube at this time, within this circle in the tube at this time, within this circle in the tube at this time. Go execute. And the agents are pretty good at tracking that. So long as that works out, they don't have to talk to each other. They stay information without talking to each other, which is pretty impressive. If any one agent can't do that because its wheels are sleeping more than we expect, because there is a rock that's obstructing the tube, so it has to go outside, then the agent tells the others, hey guys, stop. We need to come up with a new plan. The stop command is just a few bits, so we are comfortable sending that while the agents are driving, and replanning with RT takes, low to mid single-digit seconds. So this gives us a high operational tempo, and it moves us from having a multi-hertz loop between the agents to having a loop between the agents that if we're in a parking lot will be 0 hertz. The agents will just follow their trajectory. And even in a cluttered environment, JP will talk about testing in a moment, this loop, we never trigger. We trigger every tens to hundreds of seconds. So it's 100-fold reduction or 1,000-fold reduction in communication and very good driving performance. Yeah, we are going to be driving through the lunar daytime. As you know, the moon gets 14 days of sunlight followed by 14 days of darkness. So good news is the sun doesn't move very fast in the sky. Bad news is there is no atmosphere. So early and late in the day, you get really sharp or really long shadows. And you can't see into them because, one of the reasons we can see into shadows on Earth is through light scattering from the atmosphere. No atmosphere, no light scattering. So we need to cope with a number of different environmental conditions. So we do automatic exposure correction. With front and stereo camera, what if there is a shadow in front of you and you can't see anything? Well, you automatically switch to the back stereo camera, and at least you maintain visual odometry. And since we care about the relative location of the agents, we continuously collect ultra-wideband distance measurements between the agents, which allow us to correct for drift. How do we simulate these harsh lightning conditions on Earth? By driving at night on Earth with spotlights. We have the Marsyard, which Joel mentioned he visited. We have spots light low to the ground that allow us to have very long shadows. And, lots of people, including JP, spent lots of very long nights in the Marsyard, sunset to almost sunrise, trying to demonstrate successfully that, spoiler alert, this works, that we can drive even in presence of these harsh shadows. How do we merge information from multiple agents? We do that through MoonDB. So every agent collects the information it has, it builds a local map, it keeps that local map on board. We feed this information into a distributed database called MoonDB. When we need information from all the agents, we can sync individual tiles collected by the rovers to the leader, and then the leader can merge them down. We actually do that on the GPU that we have on board, which gives us 100-fold speed up, more than 100-fold, with respect to doing it on the CPU. And I want to give a shout out to RPI for actually implementing it in his free time, and then putting it on GitHub. And randomly, we found this library that does exactly what we need, that some Croix did on put on GitHub. Why I said we keep track of individual tiles from the agents. Why do we do that? Well, because we have the ability to recompute and reoptimize past poses of the agents to correct for drift after the fact. If we correct it for drift in pose but not in maps, there would be rocks we see twice. There would be agents past locations that show up as obstacles. So we keep in sync into MoonDB past maps that the agents have collected and past poses of the agents, so that when we reoptimize past poses of the agents, we readjust maps as we go. Again, it's done on the GPU, it's fast enough that it doesn't matter, and it's open source. Come see our JP's talk at the Flight Software Workshop to know more about this. How do we prepare for loss? We don't want to have single points of failure. We want to lose the leader and just shrug our shoulders and keep driving within a few seconds. But we also don't want to synchronize information across all agents. The way we do that is we elect a leader every 10 seconds. The leader is the one that receives data from all agents. The agents keep their own data on board locally. So if a new leader shows up later, they can still brief the leader on what they've seen. But where does the leader's information go if the leader is a rover? Well, every 10 seconds, we also elect a designated survivor, which is the agent that the leader syncs information. And we have a hot mic. One. And, or if that was a question, feel free to unmute or put it in chat. We have designated survivor. If the leader is lost, a new leader will be elected. There is a weighting metric in there, and choosing the designated survivor has a strong weight, so that we don't need to synchronize as much, and every piece of information we collect is in at least 2 places, which protects us against loss. And when you put it all together, this is what it looks like. Rovers exploring the moon, roaming away from their lander, the beautiful Earth in the background.
Yeah.
Back to you.
Yeah, so we'll leave watching the amazing animation of our mission as an exercise to the reader, so to speak. And we'll dive straight into bringing you up to speed on our latest results. First of all, earlier this year, we had delivered the flight hardware. So here's a really great set of pictures to show you all the different components that we had to build to build this multi-agent system. I spoke a little bit about the top left about the deployers that are used to lower the robots to the surface from the lander. There's the base station, which stays connected to the lander and is our way of communicating between the rovers and Earth. And then certainly, take the middle picture and multiply by 3 to get our team of 3 rovers. That's what they look like. And then the situational awareness camera is all the way on the right. We have a lot of tests that we've done with the system, and here is a deployment test of the system from all the way from the deployer down to the ground, and you can see that we're often quite gentle with our robot. This is flight hardware, so we have to be very careful with it. But there are also other tests that require us to be not as gentle. So, for example, in this test, you can see that we have to violently shake our robot and make sure that it passes all of the vibration checks that need to be done for launch.
I liked it so much we did it twice.
Yeah. And there's also, I think earlier I pointed out, just on our top deck, we have a number of antennas. So there are certainly chambers for us to do all of this interference testing for both the electronics on board as well as any sort of radio transmission that we want to do with the robots. And then also you got to think about the ground penetrating radar, which is another thing that has to transmit and receive while we're driving, while we're communicating. So quite a bit of testing went into that as well in this particular chamber. And then this is also really a fun test in a fun chamber. This is what we call TVAC, or thermal vacuum chamber. So we're able to generate a vacuum in this, and also to test the robot at the range of different temperatures you're going to have, right? So they're going to experience incredibly cold, all the way to incredibly hot. I think on the lunar equatorial region, it gets up to 120 Celsius, which is why also we have to have this like sleep-wake cycle that Federico talked about. One of the really cool things to mention here, aside from, you get to see the robot harnessed up inside of the TVAC chamber, is that we have these calibration targets in front of the robot to check that our stereo cameras don't get uncalibrated as a consequence of a change in the thermal environment. And in fact, what I really appreciated is that our engineers had to go and instrument the targets themselves. So there's a thermal probe on the target, because you have to account for the fact that the calibration target actually warps with temperature. So that was something that they needed to go figure out so that they would get accurate measurements on the change in calibration. So back to you.
Yeah, so a few more tests. This is the cool robot videos fraction of the talk. All these tests culminated in a multi-agent autonomy test. Note the date, December 22nd, 2023. I think we're supposed to be done a week before, but we went all the way into the holidays, where we were able to demonstrate formation driving with wake-sleep cycles. So we're able to demonstrate one cycle of autonomy, 130-minute driving cycle on the actual flight hardware, except in the clean room. So what you're looking at is, of course, on the left on the team. On the right, you can see our 3 rovers. You can see the ground. Since our rovers know where they are by using visual inertial odometry, we had to have our interns print out a very large number of lunar textures on ESD safe, special, very expensive ESD safe paper, and then tape it to the ground, because that paper only comes in 8.5 by 11. We had some obstacles that we put in, also wrapped in paper, and we went ahead and had the rovers drive to demonstrate that they'd be able to successfully, stay in formation, recognize an obstacle, see that they could not plan through the obstacle, stop, replan around it, and move. How did that go? It went pretty well. So you saw that image. This is the onboard video from the 3 rovers and some visualization of the maps that the rovers built. And this is a longish video, so I'm not going to play it through the end, but you can see that it went well. One thing that's eerie about this test is, when talking to the test operators, they typically want really specific, cue notes. What do I need to do? What do I need to do to get the robot to do X? What do I do at this point? And for this test, those are really sparse. It's like set up the system, initialize the pose, then press enter, and whatever happens, do nothing. The point is that you have to do nothing. If you touch them, then it's no longer autonomy. So some jarring conversations, and you're like, but are you sure it's going to work? And they're like, pretty sure. So it did work, and we were able to demonstrate working indoors. Now, this is great, but it's still pretty flat, and the textures are fake. So you don't take your flight hardware outside. It gets dusty on the moon. Moon dust is okay, Earth dust is not okay. But we also have a set of development models that we get to drive outside. It is actually a more recent video where you can see the same behavior you saw here, but in a sandy, rocky environment. This is sped up, of course. But you see that we've been able to demonstrate the same behavior with natural lighting outside, with the kind of terrain wheel interaction that you expect to find on the moon. And I want to emphasize that the rovers are not only driving information, they're also making decisions about, let's take a slightly longer nap because rover 3 is a little too warm and needs to cool down. Now we should stop because our batteries are getting low. So we'll see you in 20 minutes and then we'll continue driving. This is all done with no human intervention whatsoever. Some more fun tests. We talked about exploration. This is a nighttime exploration test where we're trying to show exploration with harsh shadows. On the right, you see a visualization of what exploration is doing. You can sort of see that the robots have divided up among themselves the region to explore into 2 subregions, top and bottom. We didn't tell them top and bottom. We told them this big rectangle is what you should explore, figure it out. And then within each region, the robots are deciding where to go next. They're driving around, they're getting to the next waypoint, and they're continuing to do this until the entire region has been explored. You can't imagine how cool it is to, work on this for years and go from whiteboard to this, and then realize, well, the next step is to do this, but on the moon with sharper shadows, I guess. This is our latest formation drive. This was just a few weeks ago, I believe. 12-meter drive. 12 meters is more than the rovers can drive in one cycle without stopping and going to sleep, because the thermal environment on the moon is really harsh. So that means the robots have to wake up, drive for a bit in formation, realize our batteries are getting low, go to sleep, cool down. On Earth, the cool down is simulated. On the moon, it's going to be real. Wake back up, remember where they are, come up with a new plan, and continue. And, you know, like being in a test like this where you're on console and you're just looking outside and doing nothing and it's working, pretty amazing. Yeah, I noticed that, you know, the back rover was lagging a bit because we put a crater in its path. So the front rover just stopped to make sure that they both stay in formation. No human intervention. Back to you.
So to wrap it up and leave some time for questions if there are any. You know, what we talked about today is first of all that, you know, we had to build these small scale but very autonomously capable rovers, which is, I think, one really key outcome from Cadre, is to show that you can pack a lot into a very small package. But of course, you know, our main kind of charter is to you know, advance multi-agent autonomy and build that to enable teams of robots to work together to enable new capabilities. And specifically, we're really focused on this ability to perform distributed science measurements, because that's really kind of what we want to do here at JPL and at NASA, is to be able to collect new science, and this is a system that will allow us to do that in new ways. And then I think lastly, I just want to briefly talk about is, you know, Cadre is one way to build a multi-agent system. It's definitely not the only, and I really hope that we can be an inspiration for others to go build new multi-agent systems, different multi-agent systems. You know, one thing that you can certainly think about is how would you leverage heterogeneity, right? So in our system, we have identical rovers, but you don't have to send identical rovers. You could build a system with 3 different types of rovers that work together to achieve something new. So in general, I think I'm just really excited that we're kind of entering kind of a, you know, the next set of missions in our solar system with this new tool available to us, and I just look forward to what we'll, you know, discover next.
Yeah.
So thank you very much.
Thank you so much. This was an amazing talk. So let's open the stage for questions. You can either type in the chat and I can read for you, or you can raise your hand and directly ask to Federico and Jean-Pierre. I think there is already a question from Anya.
6 questions.
Yeah, a bunch of questions, actually. Let's start from...
Let's do that.
Let's start from the first one. Are you concerned about your COTS parts not being radiation hardened?
No, I mean, we tested them in general to make sure that they wouldn't, you know, experience immediate kind of latch ups or anything like that. But our mission is also fairly short, right? It's 14 days on the lunar surface, and also the system is designed that in those parts, if we do have an event as a consequence of radiation, is that we're able to fully reset. So our system, both in terms of the hardware and the flight software and the autonomy, is built around agents being able to restart, because that's what we have to do for a sleep-wake cycle anyways. Like, we actually, during a sleep cycle, when they go to sleep, we fully turn off the computer, and the only thing that's awake is an FPGA with a watchdog that then at certain times wakes the computer back up, and then everything restarts from where it was the last. So the system is actually resilient to that.
Okay. I'll take maybe another one from Anya, then I'll do some sampling-based decision.
Yeah.
But it's how much slippage do you expect with these wheels in the regulator, the sampling side, for instance?
I don't think I have a quantitative answer to that. I think we're gonna, just based on our testing here, even in here, just in the Mars yard, with the kind of soil that we have there, which is, you know, it's not the same thing as lunar regolith. For some of the lunar regolith testing early in the project, we actually had to go to a different NASA center to go and test it in their test bed. But I would expect quite a bit of slippage. But again, I think we've built the system to be somewhat resilient to that. Again, we're using visual and inertial solar odometry to keep track, so we're not relying on the wheel encoders. And then again, the robots are working together to keep track of their own states and history of states, as well as the ultra-wideband ranging measurements, and combining that allows you to do post-graph optimization. So you can go, the team can work together to correct for drift if it's more than expected.
Great, and maybe although there is another question from Anya, which is interesting, I think, for the broader public, which is, will the visual odometry data be made publicly available? There is very little about this thing, very little data out about these things. So this could be a nice benchmark to have, or something like that.
Yeah, I think so. I think that would be. I had thought about this being a really nice piece of data to make available. We are somewhat bandwidth limited, so I don't think we will be able to capture that for the entire duration. But I'm hoping that at least for part of the mission, we'll try to capture basically every single piece of data that the robots are collecting and get that back down to the ground. Because I think it would allow us to reconstruct and improve that they did what we thought that they did. But as you point out, I think making that more broadly available would be generally beneficial.
Very nice. Then there is a question from you, June. I think Federico mentioned communication, and here the question is, how much communication between rovers, between rover and leader, etc., is required, and how robust is the scheme against disturbances in communication?
It's a really good question. Embarrassingly, I don't have a number off the top of my head, but we're talking, first of all, it's event driven. While the robots are driving, the number is between 0 and what is one packet? A few bits, but it's 1 bit for the command plus whatever the framing is. We pushed hard to minimize that amount of communication. Communication is event driven. So before we plan, we need to get the thermal and power state of the agents to the leader. That is a handful of bytes per agent sent to the leader. Before we drive, we need to send maps from all the agents to the leader. Maps are the largest data product we have. So we only synchronize them when we absolutely have to. How big of them are the maps? Well, it depends how long it's been since you last drove. I think the rate at which maps accrete is low kilobits per second, but then you're not synchronizing them until you need them. Our radios give us, order of megabits per second between them. Mm-hmm. So we can drive without communicating for a long time and then sync. How robust is the scheme against communication disturbances? Fairly robust, in that a lot of work went into what happens if we are unable to sync a given piece of information. Well, we'll sync with whatever we will plan with whatever we have. What happens if we plan with stale information? It will be a bit suboptimal. For exploration, that means we may not plan around, we may explore a region twice. For formation, it means we may miss a rock that's off in the distance and then have to replan again once we get close to that rock. If we don't have thermal and power information from an agent, that's a bigger deal, because you may come up with a plan that's a bit too optimistic for that agent. But the agent won't blindly execute it. If an agent realizes on board that it's going to violate its thermal or power constraint, it's going to trigger a stop and a replan. So we'll always be safe, although we may be suboptimal. That's
very interesting. And yeah, it's challenging. It's so interesting to hear this. Maximilian had another question. Oh yeah, about this concept of the designated survivor. I think when determining the health status of the swarm, how does an agent distinguish when it lost contact to the other agents between all other agents are down, or there's some general problem, or the communication problem, it actually stems from its own communication tools? for instance, this could be important to elect new leaders.
Yeah, I mean, if you've lost, so the specific answer for Cadre is that our data flows to Earth through the base station. So I fibbed a bit, we elect a leader, we can lose autonomy on any agent, but if we lose the base station, we cannot talk to the rest of the robots. This is how our hardware is built. So the agents continuously check that they have a link to the base station. They don't check that the base station is running autonomy. They don't check that the base station is healthy or anything like that. They just need that link to be able to send data back to Earth. I wish we'd been able to move past that, but it's been pointed out to me that despite my autonomy fever dreams, if you do a great autonomy demo, but you don't tell Earth about it, it doesn't count. So, if you lose contact to the base station, you assume you are the problem, because if the problem is that you lost the base station and everybody else, that's probably a failure from which we can't autonomously recover. That is the answer for Cadre. In general, you've got to decide what your threat model is. Like, a case in which you lose communication from everybody else means that either your radio's down, and if your radio's down, you are the one in trouble, or you're driven beyond the range of everybody else. And then what you want to do is plan a behavior in which you drive back toward the last known location where you had comms. And we do something along that spirit. For leader election specifically, you elect a leader among the folks you can talk to. If you are the only one you can talk to, you elect yourself the leader, which allows you to make decisions about yourself. And I don't think we put that in the tasknet in the end, but something we talked about a lot was, well, if you're the only one awake, then the one decision you should make as leader of yourself is drive back toward the last known location of the base station, because you are probably the problem. Okay.
That's super interesting. There's a lot of connections also to game theory, I think, if you start thinking about how this could self-regulate.
Yeah.
So. Okay, there are more questions coming in. Maybe I'll take some other ones. Alice is asking, do you have a way to update the firmware? If so, what are resilience measures do you use in case of failed updates?
Yeah, that's a great question. So when I hear firmware, I typically immediately think about like the FPGA, for example. So things that are fairly fixed. In that case, we don't have a way to update the FPGA. The FPGA is going to be what it is once it flies. But in terms of the flight software, we do have the ability to update the flight software on the base station and any of the other agents. That's typically kind of a key requirement that our flight software tends to have. In terms of resiliency measures, that's a good question. I mean, I think typically you build it in such a way that you don't break your ability to upload, and if you need to upload again, you can redo that. Again, for Cadre specifically, we're really going to try to avoid that as much as possible, right? Because we have a very short duration mission. It is a maximum of 14 days. The system is not. Neither the lander nor our rovers are designed to survive the lunar night. So we really only have that much time, and the bandwidth available to us for both downlink and uplink is very limited. So we're gonna, spending that on a flight software update would be, not the best use of our time. Let's put it that way. Like we rather, keep driving, make parameter changes to the system, and collect as much data as possible.
That's great. Omkar has a question asking, what radius around the base stations can the swarm travel in order to remain in contact with the base station? This is related to communication ranges.
So yes, so the radius, we have a self-imposed radius, I think, of about 100 meters.
Yeah.
The radios have a link margin that goes well beyond that. They can communicate much farther out than that radius that I just mentioned, which is a typical thing to do. You want to have margin in your link budget.
And
Okay.
yeah, again, it's a tech demo. So it's also a mesh radio system. So you could imagine, and we have imagined scenarios in which, one rover drives out to the edge of columns and then another rover leapfrogs it and goes further away. It was pointed out that, you want to demonstrate a few technologies at a time. But yes,
Yep.
Nice, nice. I have a final question that's really, I mean, I discussed a bit already with Federico, Abby, and others about this, but it's driven by my research, which is here you are designing so many different pieces. You are taking many decisions. How do you deal with the dependencies, the costs of all of these things, the repercussions of plan Bs or fallback plans? Do you have a way to always keep track of your of where you're at? I imagine also to report to the funding people, right? To the people that sponsor this thing.
that's a new question.
It is kind of a me question, but also not a me question, because
my answer is I asked the PI.
Yeah, right. Well, it's true. But I mean, I want to just point out as principal investigator, my focus has been mainly on the technology development to make sure that what we fly is a sufficient advancement in terms of the technology that makes that technology demonstration worth flying, right? So because I think you have a lot of ideas, and then you have to titrate that down into something that fits the schedule and it fits the budget, and you do that throughout the project, right? So you at the very beginning, your ideas are probably you have a large set of ideas, and then you try to figure out what fits with the system, what doesn't fit with the system, or sorry, fits with not with the system, but fits with the project's constraints. I mean, we had kind of key objectives at the beginning of the project that we wanted to meet, and I think those have actually not changed at all throughout the entire project. They were like, these are the fundamental things that Cadre needs to achieve. Now, where you get to be flexible is in how do you achieve those goals, right? We talked a little bit about how there's a continuous optimization of compromises that we have to go through. And I had to, for example, accept the fact that I wanted to fly 4 robots, but then eventually had to make do with 3 because of things that we learned about, the thermal modeling and the thermal environment of the moon that we didn't know at the very beginning. But at the same time as PI, I also had to kind of, draw a boundary. Like I was not willing to go below 3 agents, because I always said that, 1 robot is not a multi-agent system, obviously, because it's going solo. 2 are just, buddies, but with 3, you have a team, right? So at 3, we start to have a team. So that was the minimum for me. So I had to really, make sure that the team didn't optimize to the point where we had less than 3. Another way to structure these kind of things is that we had, at the very beginning, we got into clearly setting what we considered, I think we called it typically like the threshold and then the baseline. So we designed a system for the baseline, which is basically all of the capabilities. But then there's also a very clear threshold of, at minimum, the system needs to be capable of that. And we really make sure that all of our resources are focused on at least meeting the minimum threshold for that, and then obviously that threshold also contributes to you to being able to do the baseline. So and then the reality of any project is that you're going to run into schedule changes and cost changes, and pandemics can happen that have impact on the availability of chips and lead time for components and all these kind of things. Like these are all natural things, and you kind of just navigate your way through that. And the reason I talked about the PI, my role as PI, is because again, I managed that mainly from a technology perspective, right? Navigating what would we be doing during the mission, and what kind of technology would be developing, and to what extent would we develop different technologies. And but then the project manager, there's actually a dedicated project manager. They have the really difficult job of actually getting this, negotiating with the sponsor to get this done on, with the appropriate times, and with the budget and all that kind of stuff, and with the staffing and everything else. So their job is even more significantly more difficult than mine.
This is great. It's a great answer, and it's very an inspiration for the kind of research we do. So, yeah, I think it was a great talk. I don't see any other questions. I think people in the audience, you can reach out to both Federico and Jean-Pierre if you have further questions.
Yeah, anytime.
But it was a pleasure to have you, and also I look forward to seeing more from this now that things are concretizing. So that's very cool.
Yeah, I think I mentioned that I look forward to that happening at the end of 2025. So about a year from now.
Very nice, very nice. Thank you again so much. I will share the video and some pictures for PR soon.
Yeah. Thank you so
And
much.
enjoy
I
your
appreciate
day
that.
ahead.
Thank you.
Bye-bye. Take care. Ciao, ciao.